Hey everyone, this is Brian. Welcome to Wednesday, April 7th's video lecture for CSC 143. Let's start things off with a quick tour of IntelliJ and how you can get set up with the class notes so that you can run them on your own machine. Now if you don't have IntelliJ yet, I really recommend you go download it right now and get it installed because it's going to be the IDEs that we use throughout this class, and it's got a lot of really great features that we're going to be showing you throughout the quarter that you can take advantage of when you develop your own projects. You have got my version of IntelliJ pulled up. I think it's a little bit old, but the interface should look about the same regardless of which version you pick. Make sure to download the Community Edition, which is free. When I open IntelliJ, I'm prompted with the option of opening a project. And once you've downloaded the class notes for today, there should be a link in the description. You can click on Open and go visit that day's project. So I'll open my CSC 143 notes folder, pick the day, which is the name of the folder, and then hit OK. And IntelliJ is going to open that project up. On the left side, you'll see a project button, which opens the project file navigator, and which you can start navigating through the different files and folders located inside this project. The README, readme.md, is where all the class English notes will be stored. The notes that you can read through just as a guide through touring the different Java files we see in this project. And in these video lectures, we'll be covering the content of this README and how it ties into the code that I'm actually going to be demonstrating. Now, if you're lucky, IntelliJ is automatically going to figure out how to integrate this project that you've downloaded with your Java install. And one way to validate that is to right-click on this test folder and hit Run Tests in Test. If that succeeds, then you're set. It means that IntelliJ has found your Java install and knows how to run these tests, and you shouldn't have to do any extra work to start playing around and running files on your own. Now, if that doesn't work, there's a couple things that you'll need to get set up, but it shouldn't take long. Go ahead and hit File and click on Project Structure. Make sure that the project SDK setting is set to 11. Remember, Java SE 11 is the version of Java that we're using in this class. Make sure project language level is set to SDK default, which is also going to be 11. Make sure that the project compiler output has a folder. Here I've decided to make a folder called out inside the product folder that the class files generated by the Java compiler will go. Next, in the Modules tab, make sure that the source folder is marked as a sources folder by right-clicking on it and ensuring the check mark is checked for sources. If not, go ahead and click. And the third step is to make sure that the lib folder is included as a library. So that should be listed here. If it's not, you can either add it by hand by clicking on that plus button, or you can right-click on lib and hit Add as Library. Once you get those things set up, you should then be able to run the tests in test. One kind of neat thing about IntelliJ is that it's pretty adaptive to the kinds of entry points that your program can have. So IntelliJ automatically recognizes that each of these methods are individual tests, and it lets me run these methods individually directly from the IDE. But it's also smart enough to recognize when there's a main method for any particular file, and it'll put this green arrow next to that main method that'll let me run that file's main method specifically. I can also right-click the name of the file and hit Run. That's enough to get started. We're going to talk about all the cool features that IntelliJ has throughout this course, and I really encourage you to use this IDE and embrace it for all of your future Java development, because I really do think it is perhaps the best, most powerful Java IDE there is today. Okay, let's dive right in. Okay, IntelliJ is the preferred IDE of choice for this class. The IntelliJ Community Edition is completely free to use and is compatible with your Adopt OpenJDK 11 install. I've gone ahead and put a download link here just in case you haven't gotten it already. Now, you don't have to use IntelliJ for this class. You're welcome to use any IDE of your choice, though I recommend IntelliJ for a number of reasons. The primary reason is that it has really robust debugging. We're going to demonstrate how to use the debugger very soon in this video, but what I can tell you about it is that it's very smart and intelligent in how it can inspect the underlying variables and state of your program as it executes. It's also fairly easy to use and set up, and the great way it integrates into your source code makes it really easy to start debugging and stop debugging without having to do much configuration. It's also got built-in test suite support for JUnit. We can run and debug individual tests, as well as see the expected versus actual output for whatever assertions we have. We'll be talking about test suites and JUnit very soon. We've got built-in support for Git. We can even use Git entirely through the GUI menus provided by IntelliJ. If I move my mouse up and go to VCS, which stands for Version Control Software, I can actually get some interactive Git commands right inside the menus here. I don't actually have to touch the command line. Of course, I'll be showing you everything through the command line, but if you're more comfortable using these menus that are available to you in IntelliJ, you can do that as well. Finally, we've got a pretty well customizable interface. We can switch between a light and a dark theme, editor colors, keyboard shortcuts, and so forth. I've gone ahead and edited my settings to match my preferences, and you can go ahead and do that as well, and it should benefit you for the rest of this class. As a bonus, IntelliJ actually supports Eclipse project configurations. I know some of you coming from different classes will be having used different IDEs. Eclipse is one of the more popular ones, and if you're moving from Eclipse to IntelliJ, you'll be delighted to hear that IntelliJ can actually open those Eclipse projects right out of the box. So even if you ever move on to a different class that asks you to use a different IDE, IntelliJ is probably going to help you migrate those projects over. Okay, now let's talk about FizzBuzz and software testing. FizzBuzz is a fairly simple programming challenge that has become kind of an interviewing meme that filters programmers from non-programmer candidates for programming jobs. Here's how the program goes. Write a function that prints the numbers from 1 to 100 inclusive, except if the number is divisible by 3, print fizz, if the number is divisible by 5, print buzz, and if the number is divisible by both, print FizzBuzz. Now, I don't expect this to be a challenge for any of you. If you are in this class already, this program should sound trivial. But for a lot of candidates, actually, who apply for interviewing positions or programming positions, you might be surprised to hear that they might have a lot of trouble tackling this kind of problem. And I don't want you to have that kind of trouble. If this problem is intimidating to you, this class may not be for you. But hopefully, again, you all come from relatively experienced programming backgrounds. This should be no hassle at all. This should hopefully be that confidence booster I can give you at the very beginning of this class. So here's some example output. Start with the number 1, not divisible by either, so I just print 1. Same goes for 2. Then I hit 3, which is divisible by 3, so I print fizz, 4, and buzz, which is of course divisible by 5. Let's go ahead and write a FizzBuzz program. Go ahead and visit fizzbuzz.java and fill out the body of the program. I've gone ahead and also given you the problem description inside this public class FizzBuzz here. Now, you can go ahead and write this in your IDE. As an added challenge, I'd actually suggest you try doing this in front of a whiteboard without the help of an IDE or with pen and paper. This is to more simulate the, more high pressure environment of not having assets available to you. Fortunately, FizzBuzz is pretty easy to do, so I don't really care that much either way. But it's, I suppose, a nice little programming exercise you can do without very much outside assistance. Anyway, here's how I'll go ahead and set up my program. I'll just make a for loop to print out the numbers from 1 to 100 inclusive, and I'll call a function FizzBuzz that's going to return the string output of what it should be printing. Let's go ahead and take a first stab at this. I'll go ahead and clear out some of these existing function definitions so I don't cheat on this program. For FizzBuzz wrong, this is going to be my first attempt at actually implementing FizzBuzz. Let's go ahead and update this FizzBuzz call to call FizzBuzz wrong instead. And I'll make this one return the empty string. So it compiles. Now down here, let's go ahead and walk through those conditions of the FizzBuzz program. If the number is divisible by 3, I print fizz, 5, I print buzz, both, I print both. Okay, so let's go ahead and ask that. If I is divisible by 3, remember the modulo operator is a remainder operator. It asks whether or not the number is divisible, or it determines the remainder of dividing the number on the left by the number on the right. If I can perfectly divide that number on the right, then of course I get a remainder of 0. So if I is divisible by 3, I'll want to return fizz. Okay, great. If I is divisible by 5, I'll return buzz. And if I is divisible by both, return FizzBuzz. Otherwise, we'll just return the number to the string. The conversion of number to string or integer to string in Java is integer.toString, which is a static method available on the integer class, and you can pass in as a single argument the value you're trying to convert. Now let me show you something pretty clever about IntelliJ. If I hover over this yellow highlight here, it's actually telling me condition I modulo 3 and I modulo 5 is always false. So this is a big warning sign already, and it's pretty cool that IntelliJ is telling me this. And the reason it can do that is because through some static analysis, the IDE can actually infer the state of the different variables as you pass these different kinds of guard statements. So without getting too ahead of ourselves, if we think about what the IDE is doing, it's asking, if I've reached line 27 during execution, that means that I must not be divisible by 3. Same thing goes for line 31. If I reach this point and I pass the guard statements, that means I must not be divisible by 5 either. Therefore, I cannot ever be in a state where this condition is true. But let's go ahead and say we're amateur programmers. We don't really know what we're doing, and we're just following the instructions to the letter. So we'll go ahead and ignore this warning for now. Of course, this is called FizzBuzz wrong for a reason. You've probably already figured out this is the wrong part. But let's go ahead and entertain ourselves and proceed. Okay, so there's my FizzBuzz wrong. Let's go ahead and run this program. If you've got IntelliJ set up correctly, you'll see a nice little green run button next to the inMain method of this program. Let's go ahead and run it. And let's get some output. Nice. Number 1, 2, fizz, 4, buzz. Okay, it looks great to me. Fizz. All right. I think this is a working program. Let's go ahead and pretend that's the case. Cool. We're done. Let's jump back to the README. Okay. Now let's divert our attention a little bit and talk about software testing. What is software testing? Software testing is writing code to evaluate the correctness of code. We're going to do that with expectations or assertions that check the output of a program in a way of enforcing the specification for a program. There's two kinds of tests. There's unit tests that are test specific for a module or a function. Excuse me. And there are integration tests, which test large parts of a program as a whole, end to end. These two words, unit and integration tests, these are real words that people use in professional environments. My personal opinion is it can be kind of confusing where the line is drawn between these two. But because these are the two words that a lot of people say, we'll just go ahead and say that as well. Unit tests you can treat as individual tests to test individual pieces, and integration tests are the integration of the entire program combined that test the program end to end, large parts of it combined together. Okay, there's our definitions, and what I really want to emphasize is that tests are not magic. They're code. You may have not heard of software testing before. That's okay, right? And we're going to learn about what that is. But I don't want you to fall into this trap of believing that software testing in Java or any other programming language is some special functionality that's built into the language, that the language is like super smart and is black magic to us and hidden to us and it's just going to figure stuff out. That is not going to be the case. Tests are not magic. They're just plain code. Let me demonstrate. Here's a unit test that I've written for the array list. The array list is a type of automatically expanding array. Arrays in Java, by default, the primitive array, has a fixed length. If you try to exceed that length, it'll throw an exception. The array list is an intelligent array that automatically expands whenever new space is needed. So here we go. Let's go ahead and define an array that stores integer type. By the way, this angle bracket notation here is used to define a generic type, or the type associated with a generic. We'll talk about generics later, but what you need to know from the syntax here is that this array list accepts type integers. On the right-hand side, you can have the shorthand angle brackets as a way of not having to rewrite the type definition inside the angle brackets on the left, and the Java compiler will automatically infer what type it should be. So here I am constructing a new array list. I assert that the array list has a size of 0, so there's nothing in it. I'll go ahead and add the number of 500, and then I'll assert that the array now has a size of 1 because I've added that element. What is magic, what appears to be, is this assert equals right here, but I just told you it's not actually magic. I just haven't shown you the definition for assert equals yet. That is mostly what a test looks like. A basic test is composed of a function, the test itself, that contains assertions that must all pass for the test itself to pass. These assertions are not magic, they're code too. Here is a very basic implementation of assert equals. My assert equals is going to do this. It's going to take two arguments, object O1 and object O2. In Java, capital O object is the top level object that all other objects inherit from. It's one way of specifying this type can be anything. In the body of my assert equals, I'm simply going to ask if the object on the left does not equal the object on the right. I'll throw an assertion error that the assertion has failed because these two things are not equal to one another. That's really all the assert equals does. All it really does is throw an exception and verify that these two things are equal to one another. So when we run this test, my unit test, if either of these assertions fail, I should get an exception and the test itself will fail. Now I trust that many of you can actually write this code on your own. To many of you, array list is nothing new, exceptions are nothing new. You should have been able to actually write this entire block as well as the assert equals on your own if I had asked you to do it. And I emphasize this point because, again, tests are not magic, they're code. Everything under the hood in Java is just going to be more Java. Granted, there are some things like those primitive operators we talked about, those primitive types that are of course built into the language, but testing in Java is really nothing special. It's just the same as a program that is smart about how it evaluates functions that are tests and catches exceptions when those tests fail. Now, there are several testing libraries available for languages that contain all the needed components to write unit tests. It's going to be broken down into a test runner, which is a program with a main method entry point that is going to be responsible for actually running the tests. The assertion library, which is a collection of helpful assertions like assert equals, assert true, etc. So we don't have to write those assertions by hand. And in some instances, a mocking library, a program that can substitute behavior of other classes. This is one way to isolate the dependencies of one particular class so that we can test that class individually and not have to worry about any other dependent classes that it uses by mocking them out. That is, we'll just provide a stub implementation that's going to pretend it's any of these dependencies so we can isolate the behavior and the performance of one particular method or function or class. In this course, we're going to be using test runner and assertion library that come with JUnit. If you do want to keep exploring the mocking library, there's a Java library called Makito that's going to do class and method mocking, but we're not going to be using that in this class. All we're going to be using is the test runner, that is JUnit, and the assertion library that JUnit comes with. Because JUnit is an external dependency, we do have to do a little bit of project configuration to make it so that IntelliJ recognizes it and we can start importing it inside of our code. I've already shown you how to do that at the beginning of this video when we marked that folder as library code. But if you go ahead and pop open the lib folder, you'll go ahead and see the jar dependencies that JUnit needs. I've gone ahead and included these jars with every project and all these class notes, so you get them with every time you download the project notes. But if you do want to add these to your own projects, you can copy out these jars, have a lib folder, and again, make sure that lib folder is marked as library code. I've already done it, but if you haven't done it already, or if you recognize that it's not library code, it's not working correctly, you can hit add as library down here. If I try to do it again, I'll be asked if I want to do it twice. That's of course not what I want to do, so I won't hit OK. But anyway, that's really all you have to do for IntelliJ to recognize that a library is there and to ingest these jar files. A jar, by the way, is basically an archived Java class. It's one way you can pass different modules of code from one program to another. We won't really explore the depths of JUnit too much in this class. We're going to treat it as a dependency, but again, nothing in Java is really all that magical. Testing is not magical. Underneath the hood in JUnit is just more Java. It's just going to take away some of the responsibility of writing some of those helper functions that we would be needing to actually write and run tests. Okay, now let's talk about how we can actually evaluate FizzBuzz, that implementation that we wrote, and verify its correctness by having tests to enforce the output of the FizzBuzz program. Let's go ahead and go to FizzBuzz test. At the start of this file, I've gone ahead and imported org.junit.test. And what importing test does is it gives me this @test decorator that I can attach to the function definitions inside my class to let JUnit know that this is going to be a test definition. Remember that JUnit is both the test runner and the assertion library. It's not magic. The test runner is really just a main method that figures out what things are marked @test. And the assertion library is just, a bundle of functions that throw exceptions and are handled by the test runner. So we're going to abstract those things away into this nice JUnit import here. Now let's go ahead and start writing some tests using JUnit. We'll think about first what it means to print out fizz in FizzBuzz, to have those multiples of 3. Well, one way of thinking about this is every 3 numbers, that is every multiple of 3, we should be printing out fizz. So when we start to evaluate our fizz function, we should think, okay, well, why don't we just go ahead and traverse all the multiples of 3 and make sure that fizz comes out? Let's go ahead and try that now. We of course need to call that FizzBuzz function. I've gone ahead and imported it from interview.fizzbuzz. In IntelliJ, if you press the Control key, you can click on a class definition to navigate to its definition. So there I went ahead and pressed Control and clicked on that FizzBuzz class definition, and it takes us to FizzBuzz down here. For the sake of simplicity, I'm going to go ahead and copy my definition for FizzBuzz wrong into FizzBuzz down here so that we can just import FizzBuzz and not have to confuse ourselves on which one we're using. And let's go ahead and make this one FizzBuzz as well. We'll make it our goal to fix this FizzBuzz implementation down here, and we'll keep this FizzBuzz wrong as a reference. Okay, let's navigate back to FizzBuzz test and start thinking about the expectations for these multiples of 3. We can do it by hand. We can do something like assert true. Well, let's call FizzBuzz. Let's see, I assume that if it prints out 3, then fizzbuzz.fizzbuzz.equals fizz. Right? What fizzbuzz.fizzbuzz should give me, FizzBuzz is of course that function that we just defined. When I pass in 3, I should get the word fizz on the way out. Whoops, sorry about that. Okay, simple enough. Let's keep going. Assert true. FizzBuzz.fizzbuzz. Next multiple of 3 is of course 6. That equals fizz. And so forth. You can imagine us going all the way from 3 to 99 by hand just by writing these individual assert statements. But of course, that's pretty silly. We are programmers. We know what looping is. We don't have to go ahead and manually change this variable definition. Well, we can just do it by hand. Or we can do it with a loop construct that will make it so we don't have to do it by hand. Let's go ahead and do that now. Let's define our for loop for int I equals 1. Right, let's go ahead and do int I equals 3 because that's going to be our first multiple of 3. I is less than 100, plus plus, not plus plus, but I plus equals 3 since we're going up by multiples of 3. And we're going to assert that FizzBuzz.fizzBuzz of variable I is going to contain fizz. And we can actually go ahead and replace this with a static string definition we defined up here on line 10. Now, why did I use contains down here instead of .equals? As you remember, FizzBuzz on occasion should print out FizzBuzz when things are both divisible by 3 and 5. So it may not be the case that it exactly is fizz. It may be FizzBuzz, in which circumstance I should just check to make sure that the output contains fizz. It doesn't have to be a strict equality. For 3 and 6, I know those are both not divisible by 5, so we can just go ahead and leave these static checks here. IntelliJ is actually going to warn us if we're ever going to call dot equals inside of assert true, that we can convert it to assert equals. Let's go ahead and hover over that, hit simplify assertion, and have IntelliJ do the hard work for us. Apparently I can't actually interact with these tooltips, but I can press Alt-Shift-Enter and do the same thing. Or I can click on the little light bulb and then hit simplify assertion. Okay, so that's another way you can get about doing it. Generally, we'll be seeing a lot of assert equals and assert true in this class. Okay, now we finished writing our test. Let's go ahead and run it and see what happens. You'll get a nice little check mark down here that IntelliJ is going to show you, and you can go ahead and run that test individually. Great. When we start running tests in IntelliJ, we'll get a nice visual summary of what tests passed and what tests failed. When you start seeing these green check marks, that's good. It means tests are passing. Let me show you what happens when tests start to fail. What happens if I change this fizz assertion to expect buzz? Obviously not the correct expected output, but let's go ahead and run it and see what happens. IntelliJ is going to compile everything again, and then it's going to give me this orange X to let me know that that assertion has failed. What's nice about this is that IntelliJ is going to light up that test as a red exclamation point to let me know the test failed last run, and it's going to go ahead and highlight or underline the test assertion that failed specifically. So I can go ahead and jump exactly to the point in my code where I know the failure happened. When an assertion fails, the test itself fails, and the remaining assertions that are in the test don't execute. Let's go ahead and fix that back to fizz. Run the test again. And see that we get FizzBuzz test passing again. Awesome. Now that we're done defining this one, let's go ahead and fix out the buzz side of this. Remember, we went ahead and verified that FizzBuzz.FizzBuzz is going to give me fizz every time the number is divisible by 3. Now let's go ahead and do that the same thing for buzz. Okay, I'll go ahead and clear out this code that already exists so we can just walk through the process of writing this test. Assert equals FizzBuzz.FizzBuzz of 5 equals buzz, because I know 5 is only divisible by 5 and not 3, so I can expect strict equality there. But for the rest, let's go ahead and write that loop, just like we did for FizzBuzz3's test for int I is 5, I is less than 100, less than or equal to 100, because it's inclusive, I plus equals 5. Assert true that FizzBuzz.FizzBuzz of I contains buzz. Okay, that makes sense to me. I expect all my multiples to 5 to contain the word buzz. Let's go ahead and run my test and see what happens. Uh-oh, my test failed. What happened? Well, I had an assertion failed error. Let's go ahead and click on the failing test to see what happened. All right, let's pop that open. Let's pop that open. Okay, I got a whole call stack. It's basically telling me that in my call to assert true on test.fizzbuzztest.fizzbuzz5 test at line 29, there was an exception thrown, and that caused the test to fail. IntelliJ is going to highlight that particular assertion that failed and let me know that something went wrong here. Okay. It's kind of hard to tell just off the bat what went wrong. Let's go ahead and pretend that we don't know why our FizzBuzz is failing. And let's go ahead and try debugging this step by step and figure it out by examining the state of our program as it executes. This is going to be our introduction to the IntelliJ debugger. During debugging, you'll want to go ahead and set breakpoints on your program. If you click on the gutter area to the left of the line, a little red dot is going to show up. And that red dot is a breakpoint. What it tells IntelliJ is that when the code reaches that particular line, I want you to stop execution and let me examine the state of the program so I can diagnose the issue. When you set breakpoints, you can then run the program in debug mode instead of run mode. We've so far been pressing the green arrow to run the program. We can press the little bug icon to debug the program. IntelliJ is smart. It knows how to run individual tests, and it knows how to debug individual tests as well. So let's go ahead and hit debug here. All right. The moment you start debugging and you hit a breakpoint, you're going to get this big debug window at the bottom. What's happened is IntelliJ has already run the very beginning. IntelliJ has already run this very first assertion on line 26. It's gotten down to line 29, and it's paused execution at this assert true. So we've essentially suspended execution of this test so far. When we suspend execution, we can start to take a look around at what's going on. We can look at the different kinds of variables that are defined in this function. Here we see I is currently set to 5. I can mess around. I can even change I. I can even add new variables to examine. But I is really the only variable I care about right now, so let's go ahead and run it. Okay, let's keep going. There's going to be some buttons up here that let you navigate your program and make it so that you step through your program step by step and continue to examine how your program changes over time. Remember, my program is still paused right now. If I hit the green arrow in the lower left, it'll resume, but I don't want to do that yet. I want to go ahead and keep stepping until the program fails. Let's go ahead and step over, which is going to finish out the for loop and return to the top. We see I is still 5. Let's step over again. It's going to take me to the next line. Now I has been updated to 10. Okay, great. I don't see an exception thrown down here, so I can keep going. I'll step forward again. Finishes that assertion, goes up to the top of the for loop. Step over one more time. I is now 15. I step over one more time, and I get an exception. Okay, so now we've learned that the moment I reaches 15, the exception fails. That's enough information for me to want to go back and go examine the special case where I is 15. Let's go ahead and stop execution and start debugging one more time. When that exception got thrown, IntelliJ kind of put me in this internal Java state. Let's go ahead and leave this because it's not really that useful to us and go back to that FizzBuzz test. Okay, let's try that again. Let's go ahead and debug this test with that breakpoint set on assert true. We're going to step forward until I equals 15, which is right now. And rather than stepping past this assertion, which I know is going to fail, I'm going to step in, which is this button right here. What step into is going to do is it's going to take me to the function definition and allow me to step through that rather than just stepping past the line. There's a couple of function calls on this line that I can choose to step into. The one that I care about is this FizzBuzz right here, because of course that's like the meat of our program. Assert true and contains, those are library functions. I'm just going to assume those are always working correctly. Let's go ahead and dive into FizzBuzz and see what's going on. Program execution is still paused. I know that because I have this blue line and I have the resume button ready. Once again, the IntelliJ debugger is going to let me examine what's going on in my program at this current state. Execution is paused. There's a single argument available here, which is I, and I see that it's currently set to 15. In the 15 case, I'm expecting fizz and buzz to appear. So when I step through my program, I would expect that I reach this particular line at line 49. But let's see what happens. My expectation is that I'll pass these checks and reach that 49. But when I step through, oops, I've accidentally hit this very first guard statement. And on the way out, what I return is fizz. If I step through one more time, it pops me out of that function call because the return statement happened. And now it's going to compare fizz to buzz, which we of course just know, we know it's going to fail. If I keep running my program, let's see, if I keep running my program, it actually just finishes and it lets me know that the program has failed. Yeah. In fact, it just stops execution right there. If I go to the console, there's my test failure. Okay, so that lets me know that in the I is 15 case, the scenario where I is set to 15 in this loop and pass the argument fizzbuzz.fizzbuzz, I hit this failure where I accidentally reach this first guard statement and return immediately. So here's where I would be thinking about what's wrong with my implementation, why it's reaching that statement early and returning first. Of course, we've already figured it out. It's that this guard statement up here is going to prevent us from reaching this deeper statement down here, which is going to consider both cases where I is divisible by 3 and I is divisible by 5. Let's go ahead and fix that by moving that block of code up to before these other guard statements. Whoops. There we go. Awesome. We've updated our implementation so that in the case where both I is divisible by 3 and 5, we should get FizzBuzz on the way out. Let's go back to our test and run this one last time. I'll go ahead and hit run this time and not debug, and that should skip whatever breakpoints I've had set. Fantastic. I got a green check mark and my test is completed. So I've gone ahead and validated that my FizzBuzz function is correctly outputting fizz on multiples of 3 all the way up to 100, as well as multiples of 5 all the way up to 100. This kind of reassurance that software testing gives me is proof that my program is running correctly. Is it perfect proof? Maybe not exactly. In this contains method call, I never actually validate the ordering of fizz and buzz. It's possible that fizz comes after buzz. It's possible that the function returns other things other than just fizz that are not correct, but I don't really care. All I really want here is that it does print out fizz. Same thing goes for 5 down here. So while software testing is reassurance that the program is working correctly, it is not a guarantee that the program is working correctly. Software testing cannot possibly cover the entire universe of cases. As programs grow in complexity and behavior, it's going to be impossible to test every single possible input to the program as well as every single possible output. The best we can do is test to a reasonable degree to reassure us that the implementation is working as we intend it to. Consider some circumstances where a solar flare happens, a bit in my computer is flipped, and for some odd reason, the computer thinks that 5 is divisible by 3. For a moment there, my program is not going to work correctly, and it will fail. However, that test case is so rare, it's impossible to add an assertion that's like, is there a solar flare happening, right? We cannot feasibly test for the entire universe of inputs and outputs. We cannot test for all the circumstances that all programs will execute under. But what we can test is the reasonable expectations of inputs and outputs. And writing these tests is going to give us reassurance that a program is indeed working as we intend it to. Let's go ahead and write one last test, which is supposed to be our sort of integration test. That's going to do the end-to-end evaluation of our implementation here. I've gone ahead and written it out already, but as an exercise, maybe try doing this on your own. We can write this test in a slightly different way as we might for writing the implementation. What you'll see here is that this kind of looks a lot like the actual definition of FizzBuzz. If I is equal to 3, if I is divisible by 3, it should contain fizz. If I is divisible by 5, it should contain buzz. What about if I is not divisible by either of those things? That is something that we need to output and verify, right? Remember, the specification for FizzBuzz was that if it's neither divisible by either of those things, I need to print out the number itself. And that's what we can do with these sort of integration tests, is that we can check for these other cases that are expected from our program, but otherwise might not fall into exactly what the other unit tests are already covering. Let's go ahead and write that out as an exercise. I want to make sure that numbers come out of my FizzBuzz when I don't have those numbers be divisible by 3 and 5. Let's go ahead and check that now. If I is not divisible by 3, and, I is not divisible by 5, then I should assert that the number that comes out is equal to the number itself. Assert equals integer.toString of I and output. Okay, let's go ahead and run it to make sure it's working. And we see that it passes. Fantastic. With all 3 of these tests together, I can go ahead and go to the top of the class definition and click Run FizzBuzz Test, and IntelliJ is actually going to run all those tests together. Another way you can get to that is to right-click on the file, and hit run FizzBuzz test. All right, so that is our journey through writing FizzBuzz incorrectly, writing tests to evaluate FizzBuzz, debugging FizzBuzz to fix it, and then validating our program implementation via a test suite. Now I want to talk to you about test-driven development, which is a programming methodology that we're going to be using in this class for all of our programs. Test-driven development, or TDD for short, is the idea that we're going to write tests first and write code second. By writing tests first, we're forced to reason about the interface of the code being tested and the specification for its functionality. What do I mean by that? The interface, as you remember, is the set of interactions that is made available by a system. When I wrote FizzBuzz.FizzBuzz, I essentially told the world that in my FizzBuzz class, there's going to be a static method called FizzBuzz. It's going to take integers I, and it's going to return output strings. That is my interface for the FizzBuzz program. The specification is, of course, how I want FizzBuzz to behave. I said if it's divisible by 3, say fizz. If it's divisible by 5, say buzz. If it's divisible by both, say FizzBuzz. Otherwise, print out the number. In this class, we're going to be using test-driven development for all of our projects. What's going to happen is I'm going to do all the heavy lifting for you and write several test cases that are going to evaluate the interface and specification for your programs. You are going to get these test suites right out of the box. And then you're going to determine that all the tests are going to fail right out of the box. That, of course, is expected. You don't have a working program, so all the tests should fail. But as you work on those tests over time and review the tests that are failing, you implement those different kinds of functionality, you'll start to see that tests will slowly pass. And over time, as you develop your program, you get more and more passing tests until finally you have a correct program that has all the tests passing. The great thing about having test suites in your software is that you get an excellent feedback loop during development of whether or not you're doing the right thing. Without tests, programming is kind of a shot in the dark. You don't necessarily know what bugs or other little quirks that your program has. With tests, you get the reassurance that what you've done is working correctly. You get the reassurance that when you run particular functions or functions combined together, they're going to behave as you intend, where the inputs are one thing and the outputs are another thing. That's really the magic of test-driven development, and we're going to see that when we review Project Zero. That being said, software testing is not foolproof nor perfect. Tests are not a substitute for a formal proof of correctness. There are classes that you may take in the future about formal proofs for certain theories and definitions. Software testing is not that. Remember, we physically can't test the entire universe of inputs and outputs. Similarly, tests may not necessarily cover all use cases. It's possible that you may have failed to write a test for a particular circumstance because you forgot, right? So just because we have tests doesn't mean that we necessarily have a guarantee of correctness. It just means it behaves as we would expect it to under the circumstances that we are considering. The tests themselves can be cheated. If I had gone through my FizzBuzz definition and manually wrote out the output for every single number from 1 to 100, I will have passed all the tests. I can, in a way, cheat the tests that way. I can tell the tests exactly what they ask of me. Anytime they give me an input, I'll just print out exactly what the exertion expects. That passes the tests, but it doesn't mean my program is actually correct. It really doesn't scale up to manually write in the output for numbers 1 to 1,000,000, right? So even though we have assertions about inputs and outputs, it's entirely possible that the system underneath that's running the program is just printing out exactly what the test expects it to. Finally, the test itself could be incorrect. I could have written a test that doesn't actually expect the right output. Maybe my program is behaving one way and my test is actually expecting the wrong thing. I'm going to get a test failure, and I may accidentally believe that my test is working right and my program is working incorrectly. Again, testing is not magic. Testing is just Java. You can have bugs in your tests just like you can have bugs in your code. And Just having tests is not going to be a guarantee that our software is working as we want it to. But having tests is good reassurance that it is, and it's a great way to enforce the expectations of what a program should be. Now I'd like to turn to a different topic, which is abstraction and interfaces. Recall the notion of abstraction, masking complex implementation details with simple interfaces. In the example I gave last class, I talked about how when I walk into a grocery store, the act of raising chickens or cattle or growing plants is all abstracted away to me. I don't have to know how to run a farm to actually purchase the items that are produced by that farm from the store. When I go into the store, I walk inside, I grab what I need, I pay the cashier with a credit card or cash, and then I walk out with the ingredients that I was looking for. We can think of the store's interface as the interactions I have with the store itself, that is, giving money to the cashier, grabbing things off the shelf, and the abstraction as me not having to worry about the little details of running a farm so I can get the benefits of what a farm produces. Classes in Java are going to be very much a level of abstraction that is going to abstract away some complex details of implementation and expose simple methods that provide a plain interface for me to use. Let's go over classes and objects. So Java is called an object-oriented programming language. And for a little bit of background, I want to talk about what it was like before object-oriented programming was really invented. Before OOP, there was procedural programming. Here's a bit of C code. I've defined a struct bread with an int temperature inside. A struct is kind of like a class. It doesn't really have methods. In fact, in C, you can't really attach native methods like you do in Java. So you can kind of think about it as just a container for a set of variables. In this case, the struct bread, the only thing it contains is a temperature variable with an integer inside. Then I've decided to define a function called toastBread. There's only one argument for toastBread, which is going to be a bread b. This star here indicates that it's a pointer type, so that if I pass in a pointer to a bread b, I'm actually passing in a number that represents the location of a particular bread instance. We'll talk about pointers in detail in a later lecture. One analogy you can think of it as right now is this is like passing in the street address for a location rather than the entire location itself. So when I have access to the location, or I know of the location of that bread, I can adjust the internal values of that bread. This arrow operator here is a dereference, which is to say a lookup. It's as if I was giving you a street address and you had navigated to that address. And what I've done is I've examined the reference b, which is a piece of bread. I've looked up its value in memory, and I've set its temperature field, which is the only field inside bread, to be whatever the temperature field was, plus 20. So in summary, I've got a bread container that only contains int temperature, and I have a function that accepts bread addresses and adjusts the temperature inside those breads by 20. So this was the style of programming before really OOP was started to take off. And you notice how there's sort of a separation between the struct definition and the interactions made available by the program. Toastbread is defined entirely without the without real bindings to the bread definition itself. What I mean by that is I can go ahead and define other sorts of methods, and the bread struct itself doesn't know or it doesn't particularly care. If I wanted to set temperatures to negative, I could totally define a function to do that. And nowhere inside bread can it argue negative temperature is an invalid temperature for bread. There's nothing preventing me from doing that. So rather than defining standalone functions, these standalone functions that are independently defined from the struct definition, these are called throughout the program. In OOP, we're going to delegate functionality to objects. And we're going to manipulate those objects via functions that those objects will directly expose, called methods. So let's take a look at how we might implement that bread interface again, but this time using OOP strategy. I'll go ahead and define a class bread. Class is much like a struct, but I can define methods on it, which are functions attached to the instance. Once again, I have an int temperature field. But this time, rather than defining a standalone toast function that accepts a pointer to a pointer to a bread, I'm actually going to define the function as a part of the bread itself. And I can call toast on the bread instance to raise its internal temperature by 20. So what's special about this definition is I've strictly attached it to the definition of the bread itself. It's not like in the C example, where toast bread was defined externally from bread, and bread essentially had no say in how toast bread could interact with it. Down here inside class bread, the toast method is exposed by the bread, and it tells users and clients of bread that this is available and it's a function that's readily callable. It's not something that it's not something that you call externally to manipulate the internal contents of the bread. A couple other things you want to think about here inside this method definition. The this keyword is going to return, well, not return, but the this keyword evaluates to essentially a reference to the current instance. So when I do this.temperature and I use that dot notation here in Java, the dot is going to look up the reference that is referred to by this, and then I'm going to get the temperature field out of that bread instance. So the corresponding analogy in C would have been this bread star, but in Java, we'll learn about how everything's a reference, and there's not really pointers like there are in C. There's not raw pointers, so to speak, but the pointer here is similar. This is kind of like an address for a location of bread, and I look up where that bread is in memory. And then down here, this is kind of like the address of an instance of bread, and I look up the value, or I look up the bread instance itself when I use the dot notation to go from the reference this dot to look up the temperature field and increment its temperature by 20. In Java, formally, a class can be thought of as a blueprint for an object. Classes contain a number of things: properties, sometimes called instance variables or fields, that define the object's internal state, and methods, functions that are attached to the object for modifying that state. In this bread example, I think it's pretty straightforward. We have a single field in temperature, and we have a single method, toast, which modifies the internal state of that bread. Let's take a look at the circle class, which I've gone ahead and defined in this notes file, circle.java. You've got public class circle. We'll talk about implements shape2D very soon. It's got a single field, radius. It's got some methods like setRadius, which assigns the radius to something non-negative. If it's negative, it'll throw a runtime exception. We've got a getRadius, which simply retrieves the radius value. We've got an area method, which returns the area of the circle, which is, of course, pi r squared. And I've also got a helper main method down here, so you can try and run this if you'd like, so I can get out the radius of this particular circle. A couple other things we want to observe in Java. This class has a constructor, which is something that we didn't see in C. The constructor is essentially a function that you have to call in order to initialize an instance of the class. So remember, the class itself is a blueprint for instances of the object, and I can use the constructor to construct individual instances. So I use my circle to define what my instances are going to look like, and then I build circles by constructing them using the constructor, and each circle itself is going to have its own little radius. Okay, let's go back to the README. So these methods are going to form abstraction by hiding the underlying changes or computations that the class is going to have to do for certain function calls. What I mean by that is, rather than having to go about figuring out how to compute the area of every single object or every single geometric shape in existence, I can go about defining the area method on those individual classes so that clients of those classes can just call that area method on their own without having to actually know how to compute the area of a circle. Remember that in circle.java, we defined the area method as returning pi r squared, and clients of circle can just invoke circle.area, well, an instance of circle.area, to get the double on the way out, that is the area of that circle. This would be different than how in the old-fashioned procedural example with the bread, I'd have to go out of my way to define a function that looked like area of circle, that accepted a circle as an argument and then defined the computation for that circle. So the nice thing about these methods that are attached to these functions is that they're isolated to the definition of the class itself. I don't have to do them separately from the structures. Furthermore, Java is going to explicitly allow us to hide properties or methods using access modifiers. If you recall in the class definition, you may have seen things like public, protected, or private. And when you declare methods or properties as having certain kinds of access, it changes the way, or it changes what other classes can see when they try to interact with that class. The three access keywords we care about are public, protected, and private. Public is an explicit statement that any other client, any other class can access this particular property directly or method directly. Protected only enables the class itself, as well as inheriting children classes, to access those properties or methods. We'll talk about inheritance later. And the private keyword explicitly requires that only this internal class can access that particular field or method. One example we saw in the circle was that private int radius. This essentially says, anytime you instantiate circle, you can't actually examine the raw radius field. You can never do myCircle.radius because it's a private field. You can do it if you happen to be inside the circle class though. So down here, I can do a setRadius because I'm within the circle class and I have my setRadius method defined within circle. But outside of circle, if I try to instantiate a circle, I cannot refer to its radius field. Take a look at this getter and setter strategy that I've applied to this circle. I've got a getRadius that returns the radius and a setRadius that assigns the radius to something. You might be wondering why I would go about creating these methods versus just making this field public. And it's not super intuitive based on perhaps this example, because there's not really that much going on. This is a pretty basic class. But what you want to do when you define your classes and you start defining a lot of these different state variables is you want to have good control over your state so it doesn't get into a bad state. One example here is I've gone ahead and added a runtime check to make sure that if the radius I'm trying to set to this circle is less than 0, I'll go ahead and throw an exception. Down here, this is a reader method that only lets you have read-only access to the radius. So what that means is another client, another section of Java code can't just go into my circle and set my circle.radius to equal to something negative. They have to go through the setter, and if they try to set it to something invalid, it'll throw an exception. And come to think of it, I should probably put this in the constructor as well, so I can never start with a circle in a bad state. So in short, having these fields private makes it so you'll have more fine-grained control over what kinds of things can change the internal state. Over time, as you build more and more complicated classes, you're going to see yourself having more of these private fields. And we keep those private not only to prevent bad accesses and bad writes, but to enable the abstraction of the item such that outside clients don't have to know about it. We're going to have maybe several more properties inside this circle, and we don't necessarily care about allowing external classes to know about the underlying information. Back to my grocery store example, if a farm has a certain number of chickens, a certain number of cows, those things are not relevant to me. And even if I'm curious about them, it's not something that that farm necessarily wants to expose. So what it's going to do instead is maybe expose things like buy eggs or buy beef or something like that, right? And it can still manage its own properties using these private fields, but it's only ever going to expose to me these publicly defined methods. Okay, now let's talk about interfaces. We've talked about interfaces already. I've mentioned how the act of me walking into a grocery store, grabbing things off the shelf, and paying the cashier, that is me interacting with the interface of the grocery store, where the interface is that set of interactions made available by a system. We said that classes are blueprints for objects. When I define a class in Java, I essentially define what all the instances of that class are going to look like. Also in Java, an interface is a blueprint for a class. So that's one level up. Classes are blueprints for objects. When I construct an instance of a class, I'm building an object that looks like and resembles the class definition. When I define an interface in Java, I'm defining a set of requirements that a class itself is going to have to fulfill. So classes we use to create objects, instantiate new objects, create them, or construct them. Interfaces we'll use to define expectations for what classes are going to look like. And here's how it's going to be done. The interface is going to describe methods a class must implement, but it's not going to describe how those methods are implemented. For the sake of this course, we're also going to pretend interfaces cannot have properties or fields. Now, outside of the scope of this class, in Java, you can have properties on interfaces, but it's a little bit strange to think about because I told you how interfaces are a set of interactions made available by a system, and it's a little strange to have properties on an interface because that suggests there's internal state for those interactions available. That's a bit too much complexity for us right now. It really doesn't matter that much. If you're ever asked about this, I would recommend you essentially give two answers. One of them is like, well, interfaces are supposed to be the methods that a class must implement. They're not supposed to have properties, but technically in Java, it is possible. Anyway, that's out of scope, so let's just pretend for now that they cannot have properties. They're just a set of methods that a class must implement. Let's take a look at shape2d.java. Here is my interface definition. I declare an interface using the interface keyword. I call it shape2d, and I declare a method definition, public double area. Okay, so what does that tell us? Well, I don't see an implementation here. There certainly aren't any curly braces available, and no return statement. So what's really going on? Well, the shape2d interface is going to describe shapes, and shapes like circle, rectangle, or whatever else we'd like to define can choose to implement this interface to let the world know that these are shape2d types. And the shape2d is going to say, okay, if you're going to implement me, you better have this double area method implemented and defined. Remember that interfaces are going to declare methods that classes must implement. It's not going to say anything about how those classes are going to implement them. So when I have a series of shape2ds, I know that the area method available is going to, well, I know that there's going to be an area method available on those shape2ds, regardless of what shape they actually are underneath. What I don't know is what's actually going to be the function or the computation that's going to determine the area of that shape. Let's go look at that circle class again and see at the very top of the circle definition, it's going to implement shape2d. When I say circle implements shape2d, Java is going to require that circle fulfills the obligations of shape2d. And remember that shape2d says all classes that implement me must have a public double area defined and implemented. We can even see how this is enforced if I go down to my area method here and comment it out. Let's go ahead and also comment out this override decorator. When I hover over this arrow that IntelliJ gives me, it tells me that class circle must either be declared abstract or implement abstract method area in shape2d. We'll talk about abstract classes in a future class, but for now, let's concern ourselves about this implementation error, which is that we're missing that area method. Circle implements shape2d. Circle is telling the world that I am a shape2d, but shape2d obligates all implementing classes to have the area method defined, as well as any other methods that happen to be defined inside shape2d. So Java is not actually going to let me compile this because Circle fails to fulfill the obligations of the interfaces it's trying to implement. One kind of cool little thing about IntelliJ, you can use its helper features to actually fulfill the obligations of certain classes. If I hover over the tooltip, I can actually click on implement methods here, and IntelliJ is going to go figure out what methods the class is obligated to implement and give you stub implementations for the file to compile. If I hit OK, what it's going to do is it's going to give me a basic implementation of that expected method area, but it's not going to return anything interesting. It's just going to return 0. But what that does for me is that it means this error goes away because now Circle indeed implements Shape2D's obligation. Of course, Shape2D never said anything about how area had to be defined. That was the responsibility of the class. So even though this area method is, computationally not true for circles, it does fulfill the expectations of a Shape2D. Let's go ahead and get rid of this and go back to my existing implementation, which has pi r squared. Let's talk about this extra little detail here, the @override decorator. You may not have seen this before. That's all right. There's certain things you can attach to method definitions to let essentially other classes know certain features about, or let other classes or the compiler know certain features and properties of that particular method. Here, the @override keyword explicitly tells the Java compiler that that area method I'm defining here is going to be overriding something. It's not required that I say @override, but it gives me reassurance that Java expects this to override something, and this indeed does override that thing. Let's consider for a moment what happens if I have a typo in area. Let's say I called area 1. Well, what I actually get here is an @override error where it says method does not override method from its superclass. Also, this also works for interfaces in this case. So Java's going to prevent me from compiling because I've defined a method, but I failed to override anything. This is especially useful in circumstances where there's already a parent class definition, and I'd like to override it, but I accidentally make a typo. We'll talk about inheritance later, but the effect of inheriting those methods that don't get overridden is that both definitions will exist because I happen to make a typo here and it fails to override the parent method. By having the @override decorator, I'm telling Java that I expect this method to override something, and let me know if I've made a mistake if it doesn't override something. This override decorator is totally optional, but it is good reassurance. And remember, we'd like to see compile errors before we see runtime errors. So it's always a good thing to have. Great. All right, Circle implements Shape2D. Now let's see how we can actually interact with Shape2D. Let's go visit shape2dtest.java. Here I've written some unit tests for my Shape2D. I actually have a rectangle test here first. Let's actually go look at a rectangle. It's pretty easily defined. It's got a width and a height. It implements Shape2D, therefore it has an area method, which is just going to return the width times the height. One more unique property of rectangle is it has a double dimensions method, which simply doubles the width and the height of the rectangle. All right, Shape2D test. I build a rectangle with a width of 1 and a height of 2. These words here, by the way, are given to me by the IDE. IntelliJ is showing me the name of the arguments, which I think is pretty helpful. This is not actual code, the with colon right here. That's just IntelliJ helping me out. So I define a rectangle with a width of 1 and a height of 2. I assert that the width is indeed 1 and the height is indeed 2. I can set it and update those values. Then when I call double dimensions, I see that my width and my height are doubled from the last time I set them. Then I also see my area method does indeed work as I expect. 4 times 2 is in fact 8. I do have to call math.round here because rec.area is returning a double for me. It's returning a double because the Shape2D class, the Shape2D interface asked me to return a double in my definition of rectangle. If I don't return a compatible type here, it's not going to let me compile. Shape2D obligates all of its implementing classes to provide a definition for area that returns a type double. So if I go back to my rectangle and I fail to provide this double, it's not going to let me compile. I actually don't know if I'm allowed to return an int here. Let's see what happens. Looks like it's not letting me do that. Area in scratch.rectangle clashes with area in scratch.shape2d, attempting to use incompatible return type. Yeah, so it looks like Java is not going to let me actually coerce these types together. Let's go back to Shape2D test. And keep on going. Next test we have in line is circle test. I define a new circle with radius 5. Get radius works as expected. I get 5 out. Set radius to 10. Get radius works as expected. I get 10. And then if I get the area of that circle, I get 314, which is of course pi times 10 squared. 314 is of course pi rounded. Okay, so that's not anything too surprising or interesting. We've talked about how assert equals works. We've talked about how running tests works. And we've talked about how we can define methods on classes and invoke them. Let's go ahead and run those tests just to be sure. So we get green check marks, yay. Now let's talk about the interface shape 2D. Take a look at this left-hand side type definition. Up here in this previous test, I explicitly said the variable circle is going to be a type circle. I've said the variable S1 is going to explicitly be a shape 2D interface. But what's curious is on the right-hand side, I've actually constructed a rectangle and circle for S1 and S2 respectively. What that means is I can actually put a concrete definition, a concrete instance of a shape 2D where a shape 2D belongs. That makes a lot of sense. Rectangle fulfills the obligations of shape 2D. Rectangle defines an area method, which is the only method required to be a shape 2D. Therefore, I can say my rectangles are shape 2Ds. The same thing goes for the circle. The circle is indeed a shape 2D, therefore I can place it inside a variable definition for shape 2D. By nature of shape 2D having an area method that returns a double, that is the area of the shape, I can invoke the area method on the shape 2D variable without actually knowing what kind of shape is underneath. So my rectangle has an area of 2, my circle has an area of 314, and I get an abstraction of this actual area method because I don't know what the shape is underneath here. All I know is that I have an area method provided to me. Let me emphasize that a little bit further. Say we're omnipotent and we just happen to know that S2 is a circle. When I'm down here though, I can't actually call the getRadius method. Well, why can't I do that? I know it's a circle. Even though I know it's a circle because I'm the programmer, Java doesn't know it's a circle. Java only sees a shape 2D as this variable definition. So in a way, I've kind of lost internal access to what these classes are. Instead, I just get a layer of abstraction that says, okay, whatever's in here has an area method, and that's the only thing I can tell you because shape 2D only defines area. Therefore, the only method I can actually invoke on S2 is area. I can't invoke these more specialized methods because they may not actually resolve to a type that I'm expecting. Let me be even more specific. Take a look at line 50. S2 is a shape 2D, S1 is a shape 2D. I can assign types to the equivalent type, so I can actually replace what is inside S2 with S1, even though I know as the programmer that there's a rectangle here and a circle here, and I shouldn't be able to maybe say a rectangle is a circle. But that's all right. That's all right because on the left-hand side, I said S1 and S2 are going to be shape 2D types, and I can put a shape 2D where shape 2D belongs. So I can say S2, you're going to be replaced by the shape 2D inside S1, and that's okay because both of these implement the methods obligated of shape 2D, which is area, and I can go ahead and invoke the area method on S2. Let's see, I've replaced S2 by S1, which has a rectangle, has an expected area of 2. And that should run and complete. Perfect. Remember, I can call the area method because all shape 2Ds are obligated to implement area, and shape 2D itself is forming a layer of abstraction between what the shape 2D defines for us, which is all those methods, and the underlying implementation, the rectangle or the circle or any other geometric shapes I'd like to define. The great thing about this abstraction is that I don't have to know what computations I have to do to compute the area of the rectangle. I don't have to know how to compute the area of a circle. All I have to do is invoke this area method, which I know is guaranteed to be on top or be a part of these shape 2Ds. Unlike classes in Java, interfaces can't be directly constructed. Instead, an interface has to be fulfilled by a concrete class. What I mean by that is I can't say something like shape2d s1 equals new shape2d. That doesn't make any sense because shape2d says here's a bunch of methods that you'll need to implement, but it doesn't say anything about how those methods are implemented. Therefore, I can't really build a shape2d. That doesn't really make, invoking those methods that the shape2d asks of doesn't make sense because I don't have definitions for those methods. It's kind of like as if I asked you to draw an animal. You might ask, what kind of animal? Well, animal itself is an abstract idea. There's a lot of things that are animals, but whatever you put on the paper has to be something concrete. Maybe you'll draw like a lion or a tiger, right? Those are both animals, but they're concrete animals. You can't really draw something like the generic animal, which is an abstract idea. Interfaces are useful because you can let clients know that classes are going to fulfill the interface's requirements without knowledge of the underlying implementation. I don't have to know how to define the area, how to compute the area of a circle to actually invoke that circle's area method. And when I get a whole bunch of shape2ds, I don't have to know the underlying implementation of those area methods for all those shape2ds. Java has several popular library interfaces that are going to abstract away a lot of this heavy lifting for the underlying structures that we're going to be interacting with. Some ones you might have seen before. List is a very popular one. List is implemented by things like ArrayList. If we go visit this webpage, which is the official Java documentation, we can read more about the classes that implement list. Interface list is part of java.util. It's implemented by ArrayList and linked list, stack, and vector. We will learn about many of these types very soon. We'll learn more things about list and the kinds of methods that lists are obligated to provide. Lists are obligated to provide iterators. They're obligated to provide methods like remove all and so forth. So even though I may not know how those lists actually function underneath, I can know that I can invoke those certain methods. Comparable is an interface we'll be seeing as well. Comparable items are items that can be compared to one another. A class that implements comparable is essentially telling clients that I can be compared to whatever type is passed to that interface. Many things have a natural ordering to them. Numbers have a natural ordering, maybe ascending or descending order. Same goes for maybe strings if you want to sort them alphabetically. And the comparable interface tells the world that the class I'm defining can be compared to other classes. Comparable is actually quite simple. You can read more about the details of the expectations of it, but the only thing comparable obligates is this compare to method here. It says, if you're going to be comparable type, you better offer me a compare to method that can be used to compare to the other type that's being passed into the argument here. This is very much what we did when we used the big integer class. Rather than using the less than or greater than operators, we used the .compareTo method that the big integer implemented because the big integer itself was a comparable type. The third interface I want to talk about right now is the iterable interface. An iterable is something that can be iterated over. There's a lot of things that we're going to be able to iterate over in this class. You've already done iteration in your previous classes or your background experience whenever you write a for loop or a while loop. Maybe you'll iterate over an array by looking up each individual index. The iterable is going to make that action of iterating over the items more abstract. And it's going to extend the notion of iteration to objects that don't necessarily follow the strict for loop or while loop pattern. Well, what do I mean by that? In arrays, we can access individual elements via array indexing. We can iterate over an array by using indexes from 0 all the way up to the length of the array. But what about other structures that don't have indexing? What about something like a tree? We'll talk about trees later in this class, but what if I wanted to iterate over all the leaves of that tree? If you go outside, you absolutely could do that. You could pluck off all the individual leaves of a tree and walk through all of them, but it doesn't really make sense in the context of a for loop. I can't just have an index that locates each individual leaf because they're kind of ordered in this unnatural, random way. So the iterable is going to tell the world, I can be iterated over, and it's going to abstract away the actual burden of figuring out how to perform the iteration itself. For simple things like arrays, I can just use an index to walk through all the values, but for more complicated things like trees, there's going to be more advanced logic that the iterable is going to do, but not necessarily exposed to the client because remember, interfaces are a layer of abstraction. In this class, we will think of iterables a lot. An iterable is going to be something special where it's going to provide an iterator method. We're going to talk about iterators very soon when you learn about Project Zero, but the iterator can be thought of as an instance of a class that contains state that can be used to traverse a particular data structure. So back to my kind of silly tree example, imagine you hired a whole bunch of people to pluck off all the individual leaves for several different kinds of trees. You can say something like, okay, the tree itself is an iterable type. I can iterate over the individual leaves. The iterator are the people you hire. These people are going to have their own internal state. They're going to be referencing their own trees or maybe the same tree, and they're going to be looking at their own leaves in a certain order that they define themselves. So in short, the iterable says this thing can be iterated over. The iterator that comes out of the iterable is an individual instance of something that iterates over something else. And that instance itself is going to have certain states, like maybe the index that the iterator is currently using to iterate over an array, which is an iterable type. One more special thing about the iterable is that I can use the for each loop on the iterable. And we're going to see more of this in Project Zero. The for each loop is a special loop construct that's available in Java that lets us loop over items inside an iterable type without having to define an array index or something special like that. It's going to take advantage of the iterable interface that says, hey, I can be iterated over, and I'm going to allow you to do that by producing iterators that know how to iterate over my underlying structure. A class can mix and match any number of interfaces so long as it fulfills all the methods of those interfaces. The array list, for example, implements both the list and the iterable interfaces. It's telling the world that I'm a list type. I expose all the methods expected of a list. I'm also an iterable type. I expose that iterator method, and I'm going to support the for each loop because my class is something that can be iterated over, so I'm going to let you invoke that iterator method to get individual iterators out. The great thing about interfaces is they don't necessarily interfere with the class hierarchy. We are going to talk about the class hierarchy and inheritance later, but the great thing now is that I can define a class and pick and choose what kind of interfaces it should fulfill. And then external clients can see and evaluate what interfaces this class fulfills, and then invoke the methods from those fulfilled interfaces without knowledge of the underlying class behavior. All right, that's everything you'll need to actually get started for Project Zero. Project Zero is our first project in this class. It's mostly introductory. It should not be terribly difficult for you based on your background. Project Zero is going to feature some of these Java interfaces that you're going to be implementing. We're going to see the iterable, describing classes which can be iterated over. We're going to see the iterator, which is a class that iterates over a sequencer structure. Remember, the iterator is kind of like an individual you've hired to perform the active iteration, and that individual is going to have his or her own state. And the comparable interface is one that we just saw, describes classes that can be compared to one another that is ordered. So maybe strings or big integers have a natural ordering to them. I can take advantage of the comparable interface that says the compare to method must be defined here and compare a class to another instance of that class. You can check out the Project Zero definition on the website. Okay, that's all I've got for today. There's going to be an individual Project Zero briefing that you can follow up after the end of this video that's going to talk more about the project in detail. Thank you for listening, and I'll talk to you next time.